Okay, so in this video we're going to be looking at three very easy examples that show how statics works and how statics analysis is basically performed on physical systems. So the first thing we need to talk about is Newton's third law of motion. So Newton's third law tells us that for every action there's an equal and opposite reaction. And what that means is that if you apply a force, so for example, let's say you have a mass resting on top of some surface, you know that this mass is going to have a weight, and a weight is essentially mass times gravitational acceleration. So this is a force because it is measured in newtons. So this is going to give you a force acting downwards on the surface. Now obviously if that were the only force acting on this system, then what would end up happening is your block would essentially be traveling through the surface. It would actually go through the surface and it would move downwards. So by Newton's third law, what we need to establish is that there needs to be a force that acts opposite to that force, and it must have the same magnitude. So we often call this one the normal force. And the only way that this can work is that if the two forces cancel out because they go in opposite directions, then this system is in equilibrium. So this is where all of statics is essentially based upon Newton's third law of motion. So what we're going to do is we're going to start off with these three basic examples. So the first one is going to be just a mass resting on top of being held by a string, and then it is hanging from the ceiling. So the first thing we need to do is we're going to do something that is called drawing a free body diagram. So a free body diagram is essentially you draw the body that you're studying, so the body that needs to remain at rest, and then you're gonna draw the forces that are acting on it. So in this case we're gonna have two forces. We're gonna have the weight of this mass, so it's gonna be mg, and we're going to have a tension force basically on that string, so let's call that T. Now usually if you have seen any basic physics before, you will know that T must be equal to mg, so that's the easy way that we solve for it. The tension on the string will just be equal to the mass, the weight of this object. But another way, more formal way to do it is we're gonna take the sum of the forces in the y direction. We know this needs to be equal to 0. And now we're going to choose a reference frame. So we're going to choose the following set of axes. Y is pointing upwards and then X pointing to the right. So basically our forces are going to be positive if they're going upwards. So in this case we notice that T is going upwards, so that needs to be a positive force. But mg is going down, so we say T minus mg. And that should be equal to 0. And now you solve for T. So T is going to be equal to the weight, so mg. Now that's very straightforward. We know that the tension is going to be that, and then if you break this down, you know that the tension coming from the top on the ceiling is just going to be T as well. So that's just a basic example of equilibrium. Now let's look at a slightly more complicated example. So we have two masses of different magnitudes, so each of them is going to have a different weight. So once again, let us essentially just choose a reference frame or just a coordinate axis, some coordinate axis, and let's draw the free body diagram of this. Now what happens with free body diagrams is that you need to do them individually, so each object needs to be treated individually. So we usually start off with the one that has the least amount of forces acting on it. So in this case M2 is the one that has the least amount of forces acting on it. So we draw the free body diagram for M2. So M2 is going to have its own weight, so that's one of the forces acting on it, it's pulling on it downwards. And now we're going to have a force that is acting on it upwards, and that force is going to be essentially the tension here. So let's call it tension 2, just to say that's the tension for mass 2. So applying the equilibrium equations, we know that for this case we're going to have T2 is going to be equal to M2 times G. So that's the tension force on this piece of string. Now let's have a look at M1. So let's draw M1 right here. Now we're going to have the mass of M1. So this is going to be M1 times G. That's the the weight of this object. But hang on, we now have a string, and this string is pulling down, because if this is going up, then the string needs to be pulling down from the top here for this equilibrium condition to be met. So we're also going to have another force, and I'm just going to draw it next to it here, but essentially they're just both acting about the center here. This force is going to be T2, which is M2 times G. Okay, so, and they're both pulling down on it. And now we have a tension force that is essentially on this part of the string. So now we need to solve for that. So let's draw the sum of the forces in the y direction. And we know that upwards is positive, so this needs to be equal to 0. And then we're going to have T1, that's the force going up, minus M1G, minus M2G. That should all be equal to 0. Solve for T1, and this is going to give you M1 plus M2 times G. So as you might expect, the tension on this string here is just going to be the combined weight of those two masses. And we just found out by using basically this logic that we separate the two bodies, analyze them separately using their free body diagrams, and then just add up the forces in the end. So this is one way to do it. Another way we could have done it is just add up the two masses, and we know that that's the total weight that is going to be acting down at this point, and then we can find the tension in one. But then for the tension in the second string, obviously we need to know what the forces are in the body here. So this is how you find forces acting on bodies based on a multi-body system. Okay, so now the last example is going to be this one. So this one is once again going to be a little bit more complicated than the other two, but hopefully it would all turn out to be quite nice. So we're going to draw the free body diagram. So we're going to have our mass here. Now we're going to have the weight of this object, which is M times G. And now we have two strings that are basically fixed to the ceiling here, and each of them is made at an angle different with the horizontal. So if we choose a reference set of axes, y and x, then we know that these forces are going to have two components. So basically we're going to have one force going off like this at some angle beta, and let's call this tension 2. We're going to have another force here, let's call this tension 1, and the angle with respect to the horizontal is going to be alpha. So in this case, we need to make sure that we can actually solve for T1 and T2. So the first thing we can do is we can say, okay, let's take the sum of the forces in the y direction. Let's take the sum of the forces in the y direction, make that equal to 0. And now you're going to have the vertical components of these vectors, which you know are going to be T1 times sine of alpha. So this just comes from trigonometric relations. We know that this vertical component is just going to be T sine alpha plus T2 sine beta. And then we have the weight that is going straight downwards here. So that's going to be mg. So in the end, we know that T1 sine alpha plus T2 sine beta are both going to be equal to mg. So that's very straightforward. Now, in the case of the x direction, we're going to have the sum of the forces in the x direction also need to be equal to 0, because remember that these forces both have a horizontal component. So we need to make sure that they both add up to 0 in the end. So T1, the horizontal component, is going to the left, so we have minus T1 times cosine of alpha. And then we're going to have plus T2 cosine of beta. So that means we can draw the relationship T1 is going to be equal to T2 over, that's going to be T2 cosine of beta over cosine of alpha. So we just solve for one of the tensions. Now we plug this back in here and we can solve for T2. So let's do just that. So this is going to be equation number 1. It's going to be equation number 2. Substitute 2 into 1, so we get the following. T2 cosine of beta. Now we have sine alpha over cosine alpha. That gives us tan alpha plus T2 sine beta equals to mg. And now we can solve for T2, so we know that T2 is going to be the following: mg over cosine of beta tan alpha plus sine beta. And this is going to be in newtons. Okay, so that sounds reasonable. We have an expression in terms of both mg and the angles beta and alpha. And now if we plug that back into equation 2, that's going to give us our expression for T1. So T1 is going to be cosine beta cosine alpha times mg cosine beta tan alpha plus sine beta. So you can see that even though this is a rather complicated expression, we just solve for it by using basic static analysis. And all we did was use these two basic equations. We haven't really taken into account any moments or any rotations because we assume there are none. There are no forces that would suggest there's rotations of this object. But we managed to find the tension in both strings, which was what we were interested in to begin with, in terms of both the angles beta and alpha and the mass of the object. And in statics, that's our ultimate goal. We take in some external parameters like angles and external forces, and we want to find any internal forces in the structure based on those external parameters. And once we have done that, we know that we have successfully solved the problem. And we'll continue with this a little bit more in the next video.